Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 17. We're talking about straight line regression, and this is part 5. So here's the overview of the chapter again, and today we're going to talk about the mean value of x at a fixed value of x. a mean value of y at a fixed value of x. Last time we talked about interpreting the slope, the test for the slope and the intercept. The test for the slope determines whether or not a straight line model actually fits the data. So does x have a influence in predicting y? And if it doesn't, if the slope is 0, if we don't reject that null hypothesis of the slope being 0, then we can use y bar as our estimate for y for all values of x. So if we do reject the test for the hypothesis that the slope is equal to 0, then we're saying that a straight line does predict, but that doesn't mean it's the best model. It could be that there's another model that fits better. So that's why we always have to look at our scatter diagram and see what the data looks like. And the intercept says whether or not we think the line goes through the origin. Okay, and so if we reject the null that beta naught is equal to 0, then we definitely leave beta naught in there. If we fail to reject it, then we verify that it really does go through. We need some points near the origin to verify that it goes through the origin, and then we may just remove that from our model. Okay. So today we want to talk about, or in this video, we want to talk about the mean value of y at a specified value of x. So besides just making inference about the slope and the intercept, we may want to make inferences about the regression line itself. And so we want to do confidence intervals. Here we're going to do something called a confidence band, but doing it by hand is very tedious. We may do some of those exercises, but usually you'll use a computer to do this. So for a given value of x, let's say x equals x naught, let's say we want to find the confidence interval for the mean first. So we want to find the confidence interval for the mean. So we're going to use y hat of x naught, sub x naught, plus or minus our t value, t n minus 2 degrees of freedom, 1 minus alpha over 2. And then we use s sub y hat of x naught. And here is the expression for s sub y hat of x naught. We did this in 2 videos ago, I believe. So s sub y given x times the square root of 1 over n plus x naught minus x bar squared over n minus 1 times s sub x squared, where s sub y given x is given by this equation, which is the square root of 1 over n minus 2 times the sum from I equals 1 to n of yi minus yi hat, quantity squared. So this is basically the standard deviation of the y's from y hat, which is the mean or estimated value, but with 1 over n minus 2 instead of 1 over n minus 1, and we talked about why we did that in that video. And that's the degrees of freedom because we're estimating both the mean and the standard deviation, or actually beta naught and beta 1 in the equation. Okay, so we have this null hypothesis, h naught, mu sub y given x naught is equal to some hypothesized value. So it looks really complex, but this is just some value that we're interested in, okay? And under the null hypothesis, that's why we do that 0 up there. We don't want you to think we're raising it to a power, so we put parentheses 0. The test statistic is here. So it's going to be y sub x naught hat minus its expected value, which is our hypothesized value, divided by the standard error of y hat sub x naught. And that was, again, given here. And then we have our rejection region. So if we're hypothesizing that we're greater than this value, so we have a greater than, then if our test statistic is greater than our critical value here, which is t sub n minus 2 degrees of freedom, 1 minus alpha, notice the difference. There's 1 minus alpha for the one-sided test and 1 minus alpha over 2 for the two-sided test. Okay? And then the sign here is the same as the sign here, but also notice we're negative. So here we would say that if this is our t, our critical value, t n minus 2, 1 minus alpha over 2, then if t, capital T, is anywhere in here, if capital T is anywhere beyond that, then we would reject for this hypothesis. For the second one, we're on the other side. So if t, n minus 2, 1 minus alpha over, or 1 minus alpha, not alpha over 2. I'm messing that up, sorry. 1 minus alpha, 1 minus alpha. We're not on the two-sided test yet. Then, and that's just messy. Okay. 1 minus alpha. So that's here. So if t is anywhere over here, then we would reject the null hypothesis. And then for the two-sided test, if you recall, we'll have negative t and we'll have positive t. And so if t, capital T, our test statistic is over here, or if it's over here, then it's too far away from the mean and we reject the null. Okay. Now, the confidence interval for the regression line over the entire range of x values. We're going to plot the upper and lower confidence bands. So I was jumping ahead of myself earlier. Up here, we're doing for the mean value, okay? So this is for 1 point, for one fixed value of x naught, or x, we're doing this test. Here, we're doing a confidence band for the whole line. And again, it's tedious. The calculation's pretty long, but there's a way to make it a little easier if you're doing it by hand. So here is the confidence interval. So no need for me to read this out to you. You can read that. Again, it's not really practical by hand for the whole range of x, so we're going to use an x naught x bar plus some value k, and then x bar plus 2k and 3k, and we keep doing that, whatever k we choose, so that we cover the whole range of x in our data. So here's an example. Find a 90% confidence band for age and systolic blood pressure data that we presented earlier. And if you remember, we had the results of, let's see, what is this, y bar here, and then we had beta 1 hat, and then we have x naught minus x bar here. And then we have, and this is hard to see, plus or minus, we have our t value, and then we have that s sub y given x value that we calculated, and then this is 1 plus 1 over n, and then we have n minus 1 times s sub x squared, and we have x naught minus x bar quantity squared there. Please verify these values on your own. So you can calculate these, look up the t value here, make sure you can get this information. So if we let x naught equal 45.13, that's x bar, then everywhere that we subtract from x bar, that becomes 0. So this becomes 0, and this becomes 0, and so it simplifies to this expression, and this gives us the confidence interval at that point, or a confidence band at that point. And notice, because we canceled those terms out, they're positive. We've made this the smallest that it can be. So the width, if this is x bar, and this is our line, our confidence bands are going to do something like this. That's not very good. I need the minimum point to be here, let's say, closest to the line, and then it comes on out. And then again, here, it would come on out like that. So it's the narrowest at X bar. Okay, so that's how we can calculate these confidence intervals and perform hypothesis tests for fixed values of X or across the whole. So we talked about the fixed value of X and doing a confidence interval for the mean value at that value of X. And here we're talking about doing the confidence bands for the whole confidence interval. Okay. Make sure to scan your lecture notes by midnight of the date listed in the course calendar. Be neat so that you can read them. Update your formula sheet with the formulas we've gone over today. If you have questions, come to virtual office hours. If you can't, then by all means email me, but send me a picture of your work and the questions so I can answer your question and get back to you. We will see you next